Hello students. So this is our video number part 4. In our previous video we have learned about the wave nature of electromagnetic radiation. That was the Maxwell's electromagnetic theory. So in our today's class we will see the particle nature of electromagnetic radiation, that is better described by Planck's quantum theory. So why only the wave nature is not sufficient for this electromagnetic radiation? Because we could describe different types of experimental facts like propagation mode of light, okay, after that diffraction, interference. This could be explained by using the wave nature. But different experimental facts like black body radiation, photoelectric effect or atomic spectra, this could not be explained satisfactorily by using the wave nature. So from that part, scientists felt the requirement of another theory, and for this reason, for that purpose, another research works that develop the idea of particle nature of electromagnetic radiation. Clear? So first we will discuss different experimental facts from where the particle nature of electromagnetic radiation was developed. So the first one is black body radiation. So this is our topic. The first part is black body radiation. So first we have to know that what is black body. So black body means actually the ideal body which can absorb or emit different types of wavelengths. Okay, it can absorb or emit different types of radiations having different wavelengths or different frequencies. So that type of body is called black body, and the radiation from that body is called black body radiation. For example, we could explain this by an experimental fact. Suppose you have taken, suppose this is not iron rod, suppose you have taken one iron rod and you started heating that iron rod. So what do you see first? So when we have started heating the iron rod, so at the initial temperature or when the temperature is very low, so then we could see that the color of the iron rod will become dull red. Okay, but as well as we are increasing the temperature, we could see that the red color will become more and more intense. That means from dull it will become deep red. Now as we go on increasing the temperature more, so we could see that at a time the red color will be changed into yellow color, from yellow to red, from yellow to white color, and at last when the temperature will become extremely high, at the highest temperature the color will become blue. So that means in any flame, in any type of flame, okay, in case of fire, so the blue part that you can see in it, that is having the maximum temperature. So from this experiment what we can conclude? We can conclude this. So initially the color was dull red, okay, from this color it will become deep red, and from here first it will become yellow to white, and finally it will be changed into blue color. So at this part the temperature was very low. So here there was low temperature, and here there is extremely high temperature. Now just remember the electromagnetic radiation spectrum, the electromagnetic spectrum that we have discussed in our earlier class. So among them which one is having higher or highest wavelength, or which one is having greater wavelength. So as we know that red colored radiations or red colored lights show greater wavelengths than the blue colored light. So that means here the wavelength is high, and here for blue colored light the wavelength is low. So what can we conclude from here? So what is the relation of wavelength, okay, with the temperature? So as we are increasing the temperature we are increasing from lowest temperature to highest temperature. So as we are increasing the temperature, the wavelength goes on decreasing, okay. So the red color is of higher wavelength and the blue color is of lower wavelength. So as we are increasing the temperature, so there will be a change in the wavelength. The wavelength will decrease, okay. That means temperature and the wavelength has an opposite relation between them. Now if we consider the frequency, then when the wavelength is high, then the frequency will be low, because wavelength and frequency, they have reciprocal relationship, okay. So from low frequency it will become high frequency. Clear? So frequency will decrease, frequency will increase. Okay. So as we are increasing the temperature, the wavelength will decrease, but the frequency of the light, the frequency of the radiation will increase. And that's why we can see or we can observe different types of color changes, okay. We can see different type of color changes when we are hitting the object. But according to electromagnetic wave theory, according to that theory, there was written that energy of an electromagnetic radiation, that depends on the intensity of the light or intensity of radiation, and not on the wavelength or not on the frequency. That means at a temperature range, if we heat a substance, then there will be increase in the temperature, but no change we could observe in its color. But that is not right, because whenever we are heating any substance, we could very evidently see the change in color, okay, and that is due to the change in wavelength as well as in frequency. So that is the experimental fact of black body radiation. So now what is the relation of intensity what is the relation of intensity with wavelength? Okay, so one more thing that is important here. So whenever we are heating any substance or we are heating any object, okay, at a particular temperature range, then that body, it is emitting various types of wavelengths, okay. It is emitting various types of wavelengths, but only we could observe one color. Why? Because among various type of wavelengths of various colors, we could see only that wavelength which is having maximum intensity, that would be prominent among all of them. And that's why whenever we are increasing the temperature, initially when the temperature was low, at that time also that iron rod was emitting different wavelengths of different color, but we could see only that of the red color, because at that low temperature the intensity of the red colored light was high, okay. So from this we would establish a relation between intensity and the wavelength. So here the curve will be like this. at a particular temperature, it will never become 0. Okay, so it will continue like this. So here, suppose the temperature is T1. At temperature T1, we are getting a curve like this. So what does it mean? It means when we are heating a substance at temperature T1, it is radiating different types of wavelength. Okay, various types of wavelengths are there. Suppose here there is a value of 100, there is a value of 200, 300, 400, 500. Okay, suppose there are different types of values of wavelength we could see in this graph. Now whenever we are heating the substance at this temperature T1, it is emitting different wavelengths. Okay, and intensity means what? Intensity means the number of particles that are of this wavelength. Suppose this point, suppose there you can see a value of suppose 20. So that means 20 particles will show the wavelength 200. Okay, 200 nanometer or whatever angstrom, whatever the unit is. So 20 particles are showing the wavelength 200. Okay, but see the maximum point of this curve. That is the maximum point of this curve. So a value between 300 and 400, suppose that is 350. So at this temperature, at this temperature we are getting the particles at a maximum amount, and that's why this wavelength is showing higher intensity. Okay, and for this purpose we could say that this wavelength, suppose it is lambda 1. So whatever the color is for lambda 1, we will see that color in maximum amount. Suppose the color for lambda 1 is red. So at the lowest temperature, that is T1, we would see the particles maximum in red colored light. Okay, we would see red colored particles in maximum amount, and that's why that substance looks red. Now the second one, suppose we are taking another temperature T2. So this is for T2. Now T2 is greater than T1. So now the maximum peak point here we are getting for a value of wavelength, that is lambda 2, and from this picture it is clear that it is suppose 250. So obviously 250 is smaller than 350. So that means lambda 2 is less than lambda 1. So whenever we are increasing the temperature, then we are getting the wavelength of maximum intensity, which will be smaller than the previous wavelength. Okay, so as we are increasing the temperature, the maximum wavelength, it will be shifted to a lower value. Okay, it will be shifted to a lower value, and that's why here lambda 2 is less than lambda 1. So this is the reason why whenever, suppose this is of, suppose any color, suppose yellow color, and that's why whenever we are heating a substance, the wavelength of the emitted radiation changes, okay, to a lower wavelength. So we will see the radiations, we will see the color of lower wavelength. Okay, that was the reason. So this is the relation between intensity and wavelength. I hope this is clear for you all. Okay, so now going to the next type of experiment, that is photoelectric cell. Photoelectric radiation, okay, or photoelectric cell, we could see the radiation that is known as photoelectric radiation. So what happens in case of photoelectric cell? So in photoelectric cell, where the light is converted into electricity, okay, where the light or the energy of the radiation is converted into electricity. So there, first of all, a metal like potassium or cesium is used. Why? Because they are electropositive metals. Electropositive metal means they can easily remove the electron from their last orbital. Okay, so they can easily remove the electron. Suppose there is potassium which is having the electronic configuration 281. Potassium is having 19, so 2881. Okay, so now what happens in this case? So now whenever we are trying to convert the radiation or the light into electricity, so first of all you have to allow to fall an incident light on the surface of a metal. Okay, on the surface of a metal. So what will happen here? This is the surface of a metal. Suppose this is potassium. Okay, in its last orbital one electron is present which can be easily removed. So suppose this was the electron. Now we are allowing the radiation to fall over the metallic surface. So what will happen now? So suppose this is the incident radiation having energy E that could be expressed in terms of Planck's quantum theory. Okay, this equation is derived from Planck's quantum theory, where h is Planck's constant and nu is the frequency of the photon. Okay, that we will discuss here in this part. So here, suppose this is the energy of the photon particle that is falling on the metallic surface. So now what will happen? So one electron will be ejected from the surface of the metal. So how would it happen? So whenever we are applying the energy from outside, so first of all it will break the bond between the nucleus of potassium and the electron. This is called binding energy. Okay, the energy that helps to bind the electron in the nucleus of potassium is called binding energy, or that is the attractive force between the nucleus and the electron. So this energy will first be used to break the bond between the nucleus and the electron, and after that it will be supplied to the electron as kinetic energy. By this the electron can move from the metallic surface. Okay, as we know that the energy related to motion of any particle, to motion of any substance, is known as kinetic energy. So here the kinetic energy will be produced in that electron. So from where it is getting the kinetic energy? From the energy of the incident radiation, the kinetic energy it is getting. So how it will work like now? So therefore this binding energy, this is also called work function. This is very important here, work function. That is important because necessarily we have to remove the electron from the metal, okay, to use it in the formation of electricity. So initially we have to break this bond, and for this reason we have to supply here the binding energy which will work to remove the electron. So that's why it is called Watt function, and it is denoted by H into nu 0. H multiplied by nu 0, where nu 0 is called threshold frequency. Nu 0 is called threshold frequency. Okay, threshold frequency means what? This is the frequency that is required to remove the electron from the metallic surface. And here one important thing, that the frequency of the incident radiation that should be greater than this threshold frequency. Only in that case we will be able to remove the electron from the metallic surface. So the condition is nu must be greater than nu 0. Okay, nu must be greater than nu 0. Clear up to this one? Okay, so now one relation we could develop from here, that is the relation is energy of incident photon is equal to binding energy plus kinetic energy of electron. This equation was developed by Einstein. Okay, so there could be a relation between them, that the energy that we are supplying with the help of the photon or with the help of the radiation, this energy, it will be used in two methods. The first part of this energy will be used to break the bond between the nucleus of the atom and the electron. Okay, first of all it will break the bond between the electron and the nucleus, and secondly it will carry the electron out from the metal surface in the form of kinetic energy. So energy of the incident photon means H multiplied by nu is equal to binding energy. It could be expressed as H nu 0. Okay, as the another name of binding energy is Watt function, so it could be written in this form also, W0. Okay, W in subscript 0, that is Watt function. So the equation is H nu 0 plus kinetic energy, that is half m v square, where mass m is the mass of the electron and v is the velocity of the electron. Okay, so now what we could write from here, or H nu minus H nu 0 is equals to half mv square. That means the difference between the energies, the difference between the energy of incident photon and that of the Watt function, okay, that will be converted into kinetic energy. So what does it mean? It means that the more will be the energy of the incident photon, the more will be the kinetic energy of the electron. Clear? So that means if nu greater than nu 0, that means the resultant value of this subtraction will become greater if nu is greater than nu 0. Okay, the more nu is greater than nu 0, the more will be the resultant value of this subtraction and the more will be the kinetic energy of the electron. Clear? And now what happens if nu is less than nu 0? If nu is less than nu 0, okay, that means the energy of the incident photon will be less than that of the binding energy. That means though we are supplying the energy, but it would not be successful to break the bond between the nucleus and the electron. Okay, so as we are not able to remove the electron from the surface, from the metallic surface, So electricity could not be generated in that case. Okay. So these are the two things that we are using in the photoelectricity or in the photoelectric cell. So from here, 4 observations we could see here, okay, that are as follows. Number 1, that point number 1 is that the kinetic energy of ejected electron, it is directly proportional to the frequency okay, frequency of the incident light also. So kinetic energy is directly proportional to the frequency. That means the more is the frequency, the more will be the frequency of the incident light, the more will be the kinetic energy of the ejected electron. So we could draw a graph like this. That is the kinetic energy of ejected electron, and if this is the frequency, okay, so it would be a straight line like this, starting from here where the value is nu zero. Nu zero means the threshold frequency or the minimum frequency of the electron. Okay, minimum frequency of the electron, from where it is starting. Now as we are increasing the frequency, so as we are increasing the frequency of the incident photon, the more frequency of incident photon, the kinetic energy of the ejected electron will also increase. Okay, the more is the frequency of the incident photon, the more will be the kinetic energy of the ejected electron. Now the next one, number 2, kinetic energy of the ejected electron, it will not depend on the intensity of the light. Intensity of the light means what? That means the number of photons, the number of particles that are present in the light. But to remove one electron, we need only one photon. Okay, to remove one electron, we need only one photon. So that means if there are so many photons present, that will not affect the removal of one electron. And that's why kinetic energy of the ejected electron, it does not depend on the intensity of the incident light or the incident photon. Okay, and so these are the main points of this equation, okay, of the photoelectric radiation. So now from here we could explain, now we could see Planck's quantum theory. Okay, so according to Planck's quantum theory, a body or a object, it discontinuously emits or absorbs the radiation, but in the form of unit, in the form of energy packets. And the energy of one packet, the energy of one unit is known as quantum. Okay, so energy of one packet, it is known as quantum. Okay, and the particle which is carrying one packet energy is called photon. Okay, so photons are the unit particles that consist the total radiation or the total energy. Clear? So one unit is known as quantum, and with the combination of this quantum, we are getting the total energy or the total radiation. So what is the energy of one packet? That is H multiplied by nu, where H is known as Planck's constant according to the name of the scientist. Okay, which is having the value 6.627 into 10 to the power minus 34 joule second. Okay, and nu is the frequency of the photon particle or of the radiation. Okay, nu is the frequency of the photon particle. So this is the energy of one quantum or one photon. So now to make the whole energy, there could be multiple of quantum. So then we could write it as n into h nu, where n is a whole number. Okay, n is a whole number. It could be 1, 2, 3 like this integer, and not any types of fraction like 2.5, 1.3, not like this. It will be only integers. Clear? So this is our today's class. So in our next class we will see the next part of these things and few problems related to the Planck's quantum theory. Okay, I hope all of you have understood today's class. Okay, thank you all for watching today's video. Have a good day.